I'd like to talk here briefly about two kinds of intermolecular forces, London dispersion forces and also dipole-dipole attractions. So one of the ideas is that polar molecules will show dipole-dipole attractions plus their special case like the hydrogen bonding. And then we usually say that nonpolar molecules do London dispersion forces. This is true, but also everything that has electron clouds can do London dispersion forces, exhibit London dispersion forces. So we want to kind of broaden our idea about that a little bit. There are two parts to the London dispersion forces. One is the electron cloud becomes polarized, and then it induces a dipole in its near neighbors and causes them to stick together. And the last question we want to look at is, which IMF is stronger? And that is a little bit more subtle than you would think. Now, dipole-dipole attractions are pretty simple. The idea is that if you have a molecule made out of two atoms where one atom is more electronegative than the other atoms, in this case chlorine is more than hydrogen, significantly more, then you get a partial negative charge at one end and a partial positive charge at the other end. And the same way any other molecules that are around will have this same situation, a negative end and a partial positive end. And you can see what's going to happen is that the negative end of one molecule will attract the positive end of another molecule. Now this is a little bit different than ionic compounds where there's a full positive and a full negative charge between each different ion. And that's going to be a very strong attraction. Here it's only partial positive and partial negative, so the attraction between these is not going to be quite so strong. Now in London dispersion forces, it's a different situation. Anything here with an electron cloud, is going to do London dispersion forces. But if we're talking about a nonpolar molecule, then the only thing it has to attract each other is London dispersion forces. For example, something like argon, or neon, something that's a nice single atom, with a nonpolar, because it's only atom, then the only thing it has to attract each other is this London dispersion forces. Well, if we have an electron cloud, we could take, let's say, just look at this one here on the left, an electron cloud. Well, the electrons are not perfectly evenly spaced all the time. At any one moment, they could be a little bit more on one side than they are on the other. And if that's the case, then it'll be a little bit negative, partial negative charge on one side, partial positive charge on the other side. So you say that's a polarized electron cloud. Now once that happens, just by accident, then the near neighbor would also be polarized. Because if you have an electron cloud, let's say this electron cloud, and if this suddenly becomes a little bit positive over here, then you could see that the electrons would tend to come over this side and make this side a little bit negative and the other side a little bit positive. So if one molecule just by chance becomes polarized, then it induces a dipole in its near neighbor. And then there'll be a slight attraction between the two molecules, and you can see that that's going to be called the London dispersion forces. Now that is similar to our dipole-dipole attractions, except that this is a permanent positive end and a permanent negative end. So this attraction will be relatively strong compared to this situation here where it's just temporary positive and negative, and the next moment that goes away. Now we can see examples of this, but here's the key idea, and the key idea is that the stronger London dispersion force is due to more polarizable electron cloud. More polarizable electron cloud. So what we have here is fluorine, chlorine, bromine, and iodine, diatomic molecules, and these are the halogens. And there's actually a nice picture of them. Chlorine you're supposed to know is a yellow-green gas, bromine is a reddish-brown liquid, and iodine is a dark purple solid, almost black. The vapor, it does vaporize relatively easily and gets a purple vapor. But for each of these examples, since we have larger and larger electron clouds, more and more electrons makes a larger electron cloud, then that larger electron cloud can be more off-center. So it is a more polarizable electron cloud. And so the London dispersion forces that are going to occur in all these nonpolar molecules will be strongest in something like iodine and be very, very small in fluorine and chlorine. So fluorine is a gas, chlorine is a gas, bromine is a liquid, iodine's a solid, and we can see that we have these different phases because they have the different strengths of intermolecular force. This has very strong intermolecular forces. Okay, chlorine must have very weak intermolecular forces. And it's all because it's a more polarizable electron cloud. You definitely want to use those words when you're talking about London dispersion forces. More polarizable electron cloud. Now, a different situation of this is if we're looking at some hydrocarbons. So these little pictures up here, there's 1, 2, 3, 4 molecules on the top and 1 molecule here. And it's methane, ethane, pentane, and hexane. And all of these are carbons and hydrogens, hydrocarbons. And this bottom one here is C20, which I think is called dodecane. Oh, no, sorry, icosane, it tells right here. And in each of these cases, they're the same size electron clouds. So we were saying before that you need to have more polarizable electron cloud. So that could either mean a cloud that is more polarizable, or it could mean that you have more polarizable electron clouds. So here, even though we have the same type of electron clouds, carbons and hydrogens, we have more of them. Each one of them can be polarized. Each one of those can attract other electron clouds just a little bit. So we see that in the effect here. The melting points, okay, melting points for the little one, very, very low, and it gets higher and higher and higher. Higher melting points. Boiling points, same thing, they get higher. And phases, you know, this would be a solid. Okay, these guys here are liquids, and these are gases. And if we were to look at things like vapor pressure would be very high for these tiny molecules and be very, very low for the larger molecules, the stronger the intermolecular force. Now, which of these is stronger, talking about London dispersion forces or dipole-dipole? Now, in general, what I would tell everyone is that dipole-dipole is stronger than London dispersion forces. I usually think of maybe about 10 times stronger than London dispersion forces, but that's not always true. And a really classic example is if we take here methane, CH4, and then if we substitute 1 chlorine for one of the methanes, we get chloromethane. If we substitute 2 of the chlorines, then we get dichloromethane. If we substitute 3 of them, we get trichloromethane or chloroform. And if we substitute 4 of them, then we have the cleaning fluid carbon tetrachloride. So I would normally have said, well, this molecule here looks like it's going to have dipole-dipole attractions just based on the shape. And here, this nonpolar molecule, the only thing it's going to have to go for it, you know, to hold things together is London dispersion forces. But we have to remember that everything has London dispersion forces. So if we say this has dipole-dipole attractions, it's dipole-dipole and London dispersion, and this guy has London dispersion forces. But if we go back and look at this, chlorine has a electronegativity of 3.0, carbon 2.5, so even though it's maybe slightly polar bond and a polar molecule, it's not very, very polar. So in this case, our dipole-dipole is not really all that strong of a force. Okay, whereas here in the London dispersion forces, we have all of these polarizable electron clouds, where here we only have these 2 large chlorines. So here, these London dispersion forces make a big difference. Now, this would be a tough idea, I think, in order to predict that. You know, if I were given these 2 molecules and asked which one is stronger, I would say, well, this is a polar molecule, even slightly polar. So dipole-dipole is generally stronger than London dispersion. But if I'm given some information, for example, the vapor pressure of carbon tetrachloride is only 11.94, whereas for dichloromethane it's 47. So this has a greater vapor pressure because more particles are able to escape. That means weak intermolecular forces. and this one has a lower vapor pressure because it must have stronger intermolecular forces. Now, the same thing in melting points, we can see that this is slightly negative, more negative, more negative, more negative, more negative. So we're saying that the melting point is larger for carbon tetrachloride than it is for the dichloromethane. And we can see that that actually is a relatively good trend, so that the more chlorines we have, the more that those London dispersion forces tend to hold the molecules together. So in this case, who is stronger? In this case, I would say that the London dispersion forces make a bigger difference than the dipole-dipole attractions. Now, there is a nice little animation, little simulation that shows this London dispersion forces. And each of these round spheres kind of represents the idea that maybe an atom is equal, the electron cloud is non-polarized, everything's equally spaced. But after a moment, you might get to something where one side's a little bit negative and one side's a little bit positive. And when that happens, then it causes its neighbors to also be polarized. So again, we say, just by chance, some of these molecules or atoms, anything with an electron cloud, will get polarized, and then it will cause polarization in its near neighbors. So this one may become a little bit negative, a little bit positive. That would cause its neighbor to be polarized, and then there would be a slight attraction. And then if this one is polarized, maybe it causes its neighbor to be polarized, and it causes so everybody gets polarized. But this is temporary. It only lasts for just a moment. Finally, we see this in this 2013 free response question. And in this question, this is question 6. They're saying here's dichloromethane and here's carbon tetrachloride. And it's asking us two questions about it. One, what's about its solubility? In the solubility for water, it's got London dispersion forces because it has electron clouds, but it also has hydrogen bonding because the bonds themselves are very, very polar. So it's a very strong case of dipole-dipole. For our dichloromethane, we can see that we're going to have a little bit of a dipole-dipole, but London dispersion forces. And in this case, we have all London dispersion forces, but pretty strong. So who's going to be more soluble in water? Well, the water has a very polar molecule, hydrogen bonding, and the dichloromethane also has dipole-dipole. So we'd expect that interaction to allow this to be more soluble. Now the second part, in terms of intermolecular forces, explain why dichloromethane has a larger vapor pressure than carbon tetrachloride. Now, if it has a large vapor pressure, that means it must have a very small intermolecular force, or smaller intermolecular force, and this must have a larger intermolecular force. So how can we account for that idea? And we go back like we were talking about, that we're saying this one must be stronger, and it must be stronger because of the London dispersion forces, because we have more and larger electron clouds that can be polarized. So this only has 2 chlorines, the other one has 4 chlorines, more polarizable electron clouds, stronger London dispersion forces would account for the smaller vapor pressure, stronger IMF. That's it.